Hey there, AP Environmental Science class. All right, I'm now going to start my Part 2 lecture on Chapter 2. We left off Part 1 talking about elements and compounds, and so now we're going to move right into organic compounds, which are the chemicals of life. Organic compound, to be an organic compound, you have to contain at least 2 carbon atoms. The exception is methane, which only has 1 carbon atom combined with 4 hydrogen atoms, CH4. But other than methane, you have to have 2 carbon atoms, and then you are considered an organic compound. Some types: hydrocarbons and simple carbohydrates. In addition, we have macromolecules, which are complex organic molecules consisting of complex carbohydrates, proteins, nucleic acids, and lipids. Now, I know you did a lot of this in bio and in chemistry. For this class, you don't need to remember the nitty-gritty details of these, but we do need to have just a baseline understanding of these compounds, so that then when we start building on with more actual environmental science type information, we'll be able to understand that information more. So again, you don't need to know the nitty-gritty here, but you definitely need to have a baseline understanding. All right, matter comes to life through cells, genes, and chromosomes. So cells, fundamental units of life. All organisms have 1 or more cells, right? You need at least 1 cell to be considered a living organism. Genes are the sequence of nucleotides within the DNA, instructions that we call genetic information, right? And this is what creates our inheritable traits. And then we have the chromosomes, which are composed of many of these genes. So here's kind of a visual of what I just talked about: your nucleotide base, okay, then forming this DNA, this double helix DNA strand that we find in the nucleus of cells, which again tell the cell, give it the instructions on how it's going to replicate and what function in the organism that cell is going to do. Here's just kind of from small to large how it works. You have genes, segments of DNA on chromosomes. Each chromosome contains a long DNA molecule in that double helix form. Specific pair of chromosome contains 1 from each parent, right? Each cell nucleus has an identical set of chromosomes in the nucleus. Every human cell, except for red blood cells, has a nucleus and therefore has DNA, has that genetic information, and a human body contains trillions of these cells, each with an identical set of genes. So that's kind of how it works from small to large when we talk about life. Again, you don't need to know in-depth information, but definitely understand, have a baseline understanding of how life is, how we deal with life, and how life forms and how life replicates here on planet Earth. All right, matter can change. We have physical change and chemical change. So remember, a physical change, this is kind of back from Earth science, no change in the chemical composition. I have a piece of paper, I rip it in 2, right? It's still paper, okay? It's a physical change. It may be smaller paper than it was before, but it's still paper. Nothing has changed chemically. A chemical change changes. You see a change in the chemical composition. So if I take this piece of paper, I'm not going to do it here in school because I'd start an alarm and sprinklers would come down on me. But if I lit this on fire, right, and burn this paper, that would be a chemical change. The paper would turn into some other type of chemical compound. So when we talk about it, we talk about in chemistry a reactant and a product. So for instance, carbon, which is a black solid, when it combines with 2 atoms of oxygen, which are a colorless gas, the product is carbon dioxide, right? 1 atom of carbon, 2 atoms combined with 2 atoms of oxygen, which is a gas, and also energy is released as well. So those are the products of the reactant between carbon and oxygen, and that would be considered a chemical change because we're changing carbon and oxygen into something totally different, carbon dioxide, and then some energy is released as well. So this brings us into the law of conservation of matter, which I know you've probably been talking about since middle school. We can change elements and compounds from one physical or chemical form to another, but we cannot create or destroy atoms. So while if I burn a piece of paper, the paper is turned into ash and smoke, it's still matter, okay? It's still the same amount of matter that we had before, same amount of atoms that we had before in the paper. It's just in a different form now because it changed chemically. But again, we cannot create or destroy atoms, and that is the law of conservation of matter. So with that in mind, what is energy and what happens when it undergoes change? Whenever energy is converted from one form to another in a physical or chemical change, no energy is created or destroyed. That's your first law of thermodynamics. So very similar to the conservation of matter. First law of thermodynamics is kind of an energy type of thing where it says conservation of energy. Energy cannot be created nor destroyed. The second law of thermodynamics tells us that we end up with lower quality or less usable energy than when we started with. And we'll talk about that more in a little bit. But basically, the second law of thermodynamics states that when you put in some energy into a system, what you're getting out is always going to be lower quality or less usable energy because some of the energy is converted into something that we usually can't use. And we'll talk again about that in just a second. So what is energy? Energy is the ability to do work. We have two types of energy. Kinetic energy, which is your energy of movement, heat, or electromagnetic radiation. We then have potential energy, which is stored energy, and potential energy can be changed into kinetic energy. So energy comes from many forms. For instance, here, this is a windmill, right? So we're taking wind and we're turning that wind into electrical energy that then would go out and be used by the population. So let's quickly talk about that second law of thermodynamics. Why is the electricity produced by wind not going to be as extensive as the wind energy? Why is the electricity going to be a little bit lower quality than the initial wind energy? Well, think, you have this windmill, right? And the windmill's turning around and producing energy. But there's friction involved, right? This is just one example. There's friction in the rotor of the windmill, maybe to the gears, okay? That friction produces heat, which is lost to the environment. We can't use that heat, okay? So while the matter or the energy is not destroyed, some of the energy is lost into the environment, and so the energy that then goes into the windmills to then create the electrical energy that we will use as humans is going to be a little lower quality than the wind itself, because some of that wind energy was used to release heat because of friction, okay? And so some of the energy is released via heat and not actually brought into the electrical system, all right? And that's that second law of thermodynamics. Here's your electromagnetic radiation. Again, gamma rays, shorter wavelengths, have a lot of energy, okay? TV, radio waves, very long wavelengths, so they have lower energy. And here we have some more potential energy. So the water behind this dam is potential energy. When that water is released, gravity takes the water from a higher spot on the dam down to a river that's usually at a lower spot below the dam, and that gravity, that potential energy, allows the water to flow and allows the water then to be produced to turn into kinetic energy, which then we can use to create power for us to use in our homes and in our businesses and in our factories. But once again, some of that kinetic energy is going to be lost via heat to friction, or maybe some other things that are going on within the dam itself. And so the energy that is actually turned into electricity going to be a little degraded, a little bit of lesser quality than the original energy. And again, there's nothing we can do about that because that's just kind of the way it works. So let's talk about energy, renewable and non-renewable. We talked about this a little bit in chapter 1. Renewable energy is gained from resources that are replenished by natural processes in a relatively short time. So clean water is a renewable energy. Timber, wood is a renewable energy, okay? Non-renewable energy gained from resources that can be depleted and are not replenished by natural processes within a human time scale. So here are your fossil fuels, okay? Your oil, your natural gas, your coal. They will be replenished over millions of years, but not really within human time scales, and so we call them non-renewable energy. Solar energy, 99% of the energy that keeps us warm and supports plants and other organisms come from the sun. Commercial energy is the energy that we sell in the marketplace. That's the energy that we're using in our homes. We supplement the sun's energy by selling energy on the marketplace. 90% of that commercial energy comes from burning fossil fuels, oil, coal, and natural gas, and that's our problem right now. We need to decrease that number. We need to become more reliable on some of these non-fossil fuel energy sources to supplement the sun's energy. We need to get away from that 90% number there if we're going to better the environment as we go into the future. Energy values and its quality. Again, we talked about this a little bit. You have your high quality energy. This is concentrated energy with high capacity to do useful work. So high temperature heat, and as an example, strong winds, an example. Energy released by fossil fuels is also an example. Coal is it's one of the most efficient ways to get high quality energy is by burning coal. The problem is it's dirty, real dirty. And that's the issue. And that's kind of the yin yang. You have coal, nice concentrated. You can get a lot of useful work, high capacity, but it's so dirty that it just pollutes the environment. Then we have our low quality energy. This is energy that's dispersed energy with low capacity to do useful work. So an example would be low temperature moving molecules. Okay, that would be a low quality energy. So again, we talked about this a little bit. Your first law of thermodynamics, also called the law of conservation of energy. Energy can't be created or destroyed. In physical and chemical changes, it just changes. It can change the type of energy, but it's not created nor destroyed. Second law of thermodynamics states energy always goes from a more useful to a less useful form when it changes from one form to another. And again, just think of friction. Okay, when you drive your car, right, you're converting gasoline into energy to drive the car. But think about heat from your engine, okay, that gets released into the atmosphere. Think about heat from the friction of your tires on the road that get released into the atmosphere. That heat we're not using to power the car. That heat is getting released. So that heat is going to degrade the actual usefulness of the energy initially coming from the fossil fuel. So again, while you don't necessarily see it, your car revved, you get the 60 miles per hour rather quickly, we are wasting a lot of that energy in, again, this form of heat, either from friction or maybe from the engine releasing that heat. Okay, and so we're not using the full potential of the fossil fuels of the gasoline that you put in your automobile. So that's what we talk about when we talk about energy efficiency. Energy efficiency is a measure of how much work results from a unit of energy put into a system. Improving efficiency reduces waste. Okay, so 84% of the energy used in the US is wasted. That's an estimate. Now, 41% of that 84% is unavoidable because of the second law of thermodynamics, which states whenever energy changes form, the changed form of that energy is going to be a lower quality. And again, this is because other items are released into the atmosphere. When that energy is changed, its form is changed, we lose some of the energy, initial energy, and that's why it's degraded. It's not as useful as the initial energy. Okay, but 43% of the energy we waste in the US is wasted unnecessarily. It has nothing to do with the second law of thermodynamics. It has to do with wastefulness on our part. And this is the number that we need to try to get down. Okay, this 41%, you're going to have a hard time getting down. Obviously, we can try to create as close to frictionless type of devices as we can. We can try to create a car engine that doesn't heat up as much. But really, where we want to concentrate on right now is the 43% of waste that we do unnecessarily. There's no reason for it. We're just wasteful, and that's what we need to try to get that number down. So what are systems and how do they respond to this change? Well, a system is a set of components that interact in a regular way. So you can think of the human body, a cell, a TV set, an economy, all right? The computer that you're watching this from, right? It's a system. It has a set of components in it, and they interact in a regular way for you to be able to see my Screencastify video here, right? Systems have inputs, flows, and outputs of matter, energy, and information. Feedback can affect their behaviors. Think about the human body. You input food, right? All right, you get energy from that food. You also get some output of matter, right? You go to the bathroom, okay? That's your output of matter, right? So again, we're just as human beings are just very similar to other types of systems in nature. And once again, feedback can affect their behavior. So Here's just a little bit of a graphic for you. Again, inputs from the environment. We have energy, matter, information. Here's your throughputs, and we'll talk about these in more detail in some chapters coming up, but those are your system processes that actually process the inputs. And then you have the output, your work or products, your waste and pollution, and in many instances, that heat that we talk about, okay, are your outputs to these systems. So we input something into the system, and then you get an output. All right, so let's talk about systems and feedback loops. We're almost done here now. A feedback is any process that increases or decreases a change to a system. There are two types of feedbacks. Positive feedback loop, which causes a system to change further in the same direction, and a negative or corrective feedback loop, which causes systems to change in opposite directions. Now, in environmental science, a positive feedback loop is not necessarily good. I know it says positive, but in many cases, they're actually bad, while the negative loops are actually good for the environment. So I want you to think about that and remember that positive feedback loop doesn't mean it's positive, doesn't mean it's going to bring good, okay? And a lot of times it brings bad, vice versa for the negative. So let's talk about it just a bit. All right, this is an example of a positive feedback. This goes back to the case study at the beginning of this chapter, to the forest in New Hampshire, where they cut down the forest. So what happens? Here we go. We have a lot of vegetation. We decrease the vegetation. That leads to erosion and nutrient loss. Well, that causes more vegetation to die, right? Which increases the erosion and nutrients loss, which causes, more vegetation to die, which leads to increased erosion and nutrients loss. Blah, 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 blah. Eventually, this is your positive feedback. You get to the point where all the vegetation has died. You can also think of ice sheets and glaciers like this, okay? Think of a glacier. A glacier has a high albedo. Remember what albedo is? Okay, it reflects a lot of the sunlight, doesn't absorb the sun's insolation, right? So what happens? You have a glacier that starts to melt. Well, if it starts to melt, its albedo goes down, right? It then begins to absorb more of the sun's insolation. Well, what does that cause? That causes it to heat up, which causes more of the glacier to melt, which causes the albedo to decrease again, which causes more of the sun's insolation to be absorbed, which causes more ice to melt, etc., 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 till you have no ice left, no glaciers left. That is an example of a positive feedback. In nature, usually positive feedbacks are not good, okay? In nature, we want negative feedback. So what is a negative feedback? Think of your thermostat at home. A negative feedback is something that instead of bringing an action to the same spot, kind of brings it back and forth. So think about it again. Think about a thermostat. You have your thermostat, let's say, set to 70 degrees. Okay, the temperature goes above 70. What happens? Your air conditioning kicks in, and that cools your temperature back down. Then you get the temperature cools back down to 68. What happens? Well, the air conditioner shuts off, the heat turns on. You then bring that temperature back up. Then the temperature gets above 70. The air conditioner comes back on. Temperature goes down. Below 70, heat comes on, etc., etc. And that keeps your temperature in your home right around that 70-degree mark, which is what you want. This is an example of a negative feedback, okay? Most systems in nature use negative feedback to enhance long-term stability, just like in your home, right? You're increasing that. You want that temperature right at 70. Same thing happens in nature. What happens, though, is we get to an ecological tipping point where the natural system stuck in a positive feedback loop can reach this point. Beyond this point, the system changes so drastically it suffers from severe degradation or collapse. And again, think about glaciers, okay? Once we get to the point where there are no glaciers left because the positive feedback has melted it all, well, then obviously you have a severe collapse of whatever the ecosystem was in that area, because now you used to have a glacier and now all of a sudden you have bare land. And that's the bad about those positive feedbacks. So in nature, we want to have a negative feedback to kind of make us stable in the long term. All right, so that's the end of chapter 2. Once again, I hope you enjoyed, and I will see you guys soon.